so now we defined a single gradient descent step, right? We know how to compute the gradient in our loss function and multiply that by the gradient in our function approximator, our state value approximation. Now, of course, in order to converge to some optimum, we need to repeat this gradient descent steps over and over again. That's the main idea behind the gradient descent process. We start somewhere in our feature space, right? This illustration is for a 2D feature space. So we start with some initialization of x1 and x2 in this example, right? Of course, we can go, usually we go to higher dimensions, but for the sake of this example, it's only 2 dimensions. We start with some assignment to x1 and x2, our tunable parameters, and then we take a gradient step and improve our function prediction or the value that is assigned to x1 and x2 until we reach a point where the gradient is 0. And that represents a local optimum, hopefully a global optimum, but you know, in non-convex problems, all bets are off usually. Okay, so how can we perform these successive steps? So a straightforward approach would be to just compute the gradient over all of our training set, over all of the states that we have an estimation of the value for that we're trying to fit. So we're trying to fit our value function to these states that we know what the values should be for them, right? That's the VS here, that's the label, the ground truth, presumably, and V hat is our estimation. So what we can do in a straightforward way would be to just compute the gradients in our approximation for all of the states that we know about, that we have a label for, and then take a gradient at that sum or the average direction that that is required for all of our observations. However, this might be, that's usually wasteful. I mean, we have very good gradients that really tell us how to improve all of our approximation over all of the states that we know of. But usually we can do it in a more efficient way. That is, once we compute the gradient for a single observation, we might as well update our estimations, our function approximator, based on a single gradient and then move on to the next one, right? And just continue this process over all of the states. That is, not compute the gradient over all of the states, but one at a time. In any case, we need to do that, and then actually do that update. Of course, the gradients will be more noisy, but the process altogether would be more efficient usually. Commonly, this is the case. This is known as stochastic gradient descent. So at each update step, so again, this follows from the observation, as I said earlier, that once a gradient on one training example has been computed, we might as well incorporate before computing the next one. And this, as I said, usually allows us to converge much faster on the local optimum, on the optimal point. And at each training step, we randomly pick one of the states, one of our samples, and update our approximation based on that. This, of course, results in a much faster process, but it's much faster. So it's
noisy.
It's a much faster process, but also a much noisier gradient at each step. And so we can further improve that, and what we usually do is what's called mini batch gradient descent. And the idea here is that we should prefer fast computations and then faster steps over more accurate steps. But the fact is that with most contemporary CPUs, we have multiple cores. specifically with GPUs that can do a lot of these computations simultaneously. So it actually will not cost us more computation time to compute gradient over several samples simultaneously, together, in parallel. So in most cases we can compute maybe 32 or 16 parallel gradients. So we might as well do that. We still have the fast computation, but now we have more stable gradients because we average them over maybe 16 or 32 samples, right? For instance, over a mini batch. And that's the idea behind mini batch gradient descent, where we pick a random subset of training examples and compute the gradient step based on that subset and then move on to the next subset. And usually we set the mini batch size based on two factors. First of all, how many gradient computations can we run in parallel, but also how stable is our gradient computation, how sensitive it is, how noisy it is to the different observations, right? If it's very noisy, then usually we need a larger mini batch in order to have a stable process, and else we can make use of a smaller one. Okay, so now we can define, once we define stochastic gradient descent and how that works, we can define our first stochastic gradient descent or approximation-based algorithm. Again, we'll start with a simple Monte Carlo approach. And here is the pseudocode. It's a fairly simple pseudocode for gradient descent Monte Carlo algorithm for estimating the state values. Alright, or for training a state value estimator, an approximator. This will be the V hat here. Okay, and in this case, we only require to have a differentiable approximation function that can take states and then also a set of tunable parameters and map those into some state value, right? A value for each one of the states. So how will this algorithm work? How this pseudocode will work? We start by initializing the value function weights. So let's call the set of tunable parameters the weights. Usually this applies if our approximator is a linear approximator. So as I said previously, in the more general case, we'll just call these theta. But here in the book, they call it W. It means the same thing, okay? Again, W is mainly for linear approximator, and we would like to be a bit more general, but for the sake of the current example, that's good enough. So we can initialize these weights, these tunable parameters in some way, for instance, all zeros, which is fine for a linear approximator. With a deep neural network, usually we want to have some smarter initialization tricks. We'll discuss those later on. Then in a Monte Carlo approach, we generate an episode, right, from S0 all the way to ST, using some policy pi, the policy that we're trying to evaluate the state values for. And so this, in the simple case, we'll just assume that we're trying to evaluate a specific policy. Later on, we'll see how we can use these estimations to improve our policy, right? And so for each one of the states that we visited, we now have a G value, right? A capital G value, which is a true sample of the sum of rewards, right, that we observed. That's just the sum of immediate rewards, discounted sum of immediate rewards from each one of the states onwards towards the end of the episode. So we have the value that we're trying to fit, the ground truth, that will be the capital G. And then we have our estimation, and the difference between them is the error in our estimation, right? Capital G minus V hat. This is also, if you remember, the derivative of the L2 loss, the squared error loss, right? And we multiply that by the gradient in our estimator. Okay, in order to get a gradient, the gradient in our tunable parameters W, towards minimizing this squared error loss. Now this process is guaranteed to converge to a local optimum because capital G is an unbiased estimate of the true state value V, right, under the current policy, the policy that we are evaluating. Okay, so let's see an example, and for our example we'll call our lovely TA, Vavar. So can you walk us through the example? I'll try to help you out.
Yes.
Okay. This is a one-step example. We have a
Pac-Man.
Pac-Man, but we have one state. This is an example that we saw earlier in this topic. We have one state where we actually observed the outcome for this state. We sampled it, and the state value, or at least the sampled value, was 10. Now let's try to fit our function approximator V hat to output something that is closer to this output, to 10. Okay?
Okay. So we represent the state here with a few features like distance to the ghost, distance to the food, and in this state, the feature space is the state is represented by 2, 2, 1. And we have our initial set of tunable parameters, theta. We set this as 0 initially. It can be arbitrarily set, but I think
so I'll just
there's a good reason for this, right?
Right. Some clarifications. So the state is represented as a 2, 2, 1 because these are the features, right? Distance to ghost number 1, distance to ghost number 2. So it's 2 for both of those, and distance to the closest food is 1.
Yes.
Okay, so it's just a way, some features to represent this specific state. Now, also important to see that our function approximator, the state value approximator, V hat, is a linear approximator. You can see you have a vector of theta, or W's in the book, in the textbook. And we take the dot product of that vector with the vector of the features. Okay, so we have 3 tunable parameters, 3 weights, 1 for each one of the features, of the 3 features that we have.
Yes.
Okay, now we initialize the feature space to all zeros, which results in a bad approximation, right? So it's just 0 instead of 10.
It'll always give us approximate value of 0, right? Because the linear sum will just add up to 0. So that's not close to what we want. We want to get 10. So how do we do this? We apply gradient descent. As you remember, this is the gradient you get applying the L2 norm and the chain rule. In this case, our initial theta is 0, 0, 0. Our learning rate is 0.1. The estimated value for the state is 10. So yes, the known value, I guess, right? The sample,
the label.
The label. This is true. Yeah. So GT here is actually the true value.
Yeah, that's 10. That's the if you can see there below. We sampled the outcome and it was 10.
Correct.
Okay.
So and our estimated value given our current known parameters would, again, like I said, be 0 because you're multiplying all the feature values by 0. And finally,
that's the dot product here.
Yes, here's
right?
the dot product.
Right.
Yes.
And that results in 0, right? The dot product results in a single value.
Exactly. So this will always result in 0. And because
not always,
because in this case, because our tunable parameters are all set to 0.
Right.
And finally, we have the gradient with respect to the output of the network and the tunable parameters. With respect to the tunable parameters. So if you take the gradient of this equation here, the theta will get cancelled and you'll just be left with fs for each one of the features. So we just get back our state here.
Right, we're taking the gradient with respect to the tunable parameters, and that's it. And then the gradient is simply the coefficient.
Yes, because
just the f's.
When you take the gradient, the tunable parameter will just get cut out. So applying this gradient now to update our tunable parameters, we get a set of new tunable parameters, 2, 2, 1. So is this any good? Is this going to help us predict a more accurate value. Let's see. So if we
so that's the example that
so
we
that's
showed.
the next one. So I'll get to that.
Right, that's the example that we showed initially. But we said, okay, we saw one state, the state over there, over there, far away. But even if we see that state, and even if we later see a state that is kind of similar, we still, in the tabular case, we didn't know anything. But now, with the function approximator, well, now we can compute the state value even for states that we never saw before.
Yes.
So let's see what would be the result now for this state, new state.
So we've learned parameters for state S. Now for S, but we're going to see what value we predict for state S prime to see if it generalizes well. Taking the dot product of the learned parameters and the features in state S prime, we get the value 13, which is close to what we got for state S, which is 10. So this shows that it can generalize to some extent, whereas in our tabular methods, we would not be able to perform this form of generalization.
Right, this function can take any state as input, right? So that's actually something beneficial for us. And hopefully it will also be accurate for new states, for states that we've never seen before. So as you can see, this is a very simple example, but it provides us with some reasonable outcome even for the states that weren't seen before. Okay, thank you, Vagal. Okay, so a side note, I guess. So you can see that in this case, in the Monte Carlo case, we did state evaluation, we learned the state value, but given a specific policy, right? We had to assume some specific policy and roll it out and then see what's the outcome. Should we really care about on-policy value approximation? And that's tricky, right? Because once the policy changes, the approximated value becomes irrelevant. Right? If you use a different policy, then these values will change or might change. But still, this is something that is beneficial for us, and we'll see this moving forward. That is policy-based approximation. It is useful still in actor critique methods or some actor critique methods. We'll discuss those later on. Although that, it might still have some issues with sample efficiency, right? If we train an approximator and then change the policy dramatically, then things might become irrelevant. But we have some tricks to change it ever slow or very gradually, and stuff like that we'll see later on. Okay, but we will consider policy-based approximation, on-policy approximation, also later.